Hi guys, I hope you're all good. A round of applause for Erez. Nice MC. Thank you, thank you. Okay, so we can teach security mechanisms how to deal with a lot of known threats, but it's a little harder to detect creativity. So, hi again guys, my name is Itamar Medyoni. I've successfully completed 26 laps around the sun. I'm a cybersecurity researcher, coder, code executioner. 10-root cybersecurity is where I'm at today as a red team operator and cybersecurity consultant. And I'm a DFIR enthusiast because aren't we all? And today I want to talk to you about the concept of direct syscalls, how it has been born, and exactly how we can combine inline assembly and direct syscalls in order to create better evasion techniques. So in order to do that, we first need to go through basic concepts that most of you probably already know, but it's important to have some common ground. So the first concept that we need to talk about is the DLL and its anatomy. So as we mostly know, DLLs are the building blocks for the Windows operating system. They contain most of Windows API. They are here to provide us with the ability to program lighter programs without re-implementing a lot of OS code. And another thing that's very important to remember is that a DLL is just like an executable file, and that is from the portable executable format. Now, the main differences between an executable and a DLL is that while an exe file would be executed by the Windows loader and mapped into a process, and then the main function of the program would be acted upon as the entry point in a DLL, it would be executed by an existing process, and one of its multiple entry points would be called to access either a function or a resource. Now, in order to resolve the correct entry point per function or resource, we have the export table, which is here to give us a list of the function names alongside their entry points in the file. Now, I'm telling you this because this is the basic knowledge you need to have if you want to talk about hooking. So what is hooking? Hooking, in essence, is the ability to add some additional logic to a function. So the best example for that is a keylogger. So if we create a keylogger, we want to have additional function attached to the function which results in pressing a key, and have that additional logic log that key to a file, for example. So the act of adding additional logic to the function is referred to as hooking, and that additional logic is referred to as the hook function. Now, we are familiar with two very common ways of hooking, one of which is import address table hooking, or IAT hooking, which is replacing the address of a function in process memory in the import address table with the address of the additional logic, and that additional logic would call the original function. The other option is inline hooking, which is replacing the first 6 bytes of the function, also referred to as the prologue of the function, with a jump to the additional logic, which will later return to the original function. Now, we already know how to deal with these two types of hooking. We can unhook and we can patch, but those methods have been proven to be quite noisy, and also some mechanisms already have fail-safes in order to ensure that we're not unhooking anything. Some of them will also rehook in case they've detected unhooking. And some of them will already alert. So we are left with the need to avoid a hook if we want to perform malicious activity, but we still don't want to perform unhooking. So this is exactly why the concept of direct syscalls has been born. Now, to understand what direct syscalls are, we first need to understand what syscalls are. So what is a syscall? As the name suggests, a syscall is system call. It's a function that is being operated by the system itself. So functionalities that reside in the kernel are wrapped as functions, and we refer to them as syscalls. And naturally, those operations would usually refer to managing processes, threads, memory, etc., or devices. Now, the question arises is, if we want to perform syscalls and we are in the user mode and this is kernel logic, how do we operate those syscalls on a daily basis? Now, the answer for that is NTdll. NTdll is what I refer to as syscall galore. It holds all the native Windows APIs, and it's in charge of managing the correct syscalls and how we call them. So now we know what syscalls are, and when we know that NTdll is in charge. So another thing that it's very important to understand is how other DLLs in the system connect to NTdll. So I want to explain that through kernel 32 DLL because it's a very common example. So if you ever opened Google and looked for any common injection API or injection technique, that you have found a lot of different flows, but they always had some 3 common functions, one of which was open process to acquire a handle to the target process. The second would be virtual alloc in order to allocate memory in that process. And the third would probably be write process memory to actually inject your information. Now, if we open any API monitor, we would be able to see that under the hood, each of these functions will call the correct corresponding function on NTdll. So for this example, open process would directly call NT open process. And we can also see by the resemblance in the signature of the functions that they have the same intent. So we can see that the return value on open process is the handle object. We send the desired access as a numeric value. We send a Boolean to say, should we be able to inherit handles or not, and another numeric value that resembles the process ID. On the other hand, on NT-open process, we can see that the handle object is being provided to the function as a pointer, and that the handle object would be populated post-call. We see that the desired access becomes an access mask object. We see that we have some more attributes that we can send to that request by an object attributes variable. And we can also provide the process ID by a client ID object. So we can see this parallelism throughout all of the common APIs that we think of when we're talking about injections, for example. So we can see that virtual alloc X would essentially call NT-allocate virtual memory, and we can see that write process memory will eventually call NT-write virtual memory. Now, this explains to us the need of kernel 32 DLL, because now we know that we are operating the exact same logic, but without the overhead of using those additional objects when calling the function. So now that we know that everything we want to do is a syscall, eventually, now we can go forward and to understand the structure of a syscall in NTdll in order to create direct syscalls. So if we look at NTdll under the debugger, we can see that all of the functions inside NTdll between the return and return instruction, or ret, are essentially the same. So we can see that in each function, all we do is move the value of the RCX register to R10, we move a number to EAX, and then we perform the syscall instruction and return. So what this teaches us is that NTdll holds no logic when talking about syscalls. It holds zero logic, and all it does is arrange the correct variables in the correct places in memory in order to pass the syscall instruction in the correct way to the kernel. And another thing that it teaches us is that NTdll holds exactly the number of syscalls. So each syscall is in ordinal order in the kernel, and each of the syscall numbers is mentioned for each function. So now that we know that, we can go on and recreate that functionality outside of NTdll in our project, and that would be what we call direct syscalls. So when we're talking about direct syscalls, essentially, what we're doing is re-implementing that assembly code in an external assembly file in our project. That code, you can see on the picture on the left, starts from the proc to the NTp instruction to mark the territory of the function. And we can see that the RCX register should be moved to R10, a number is loaded into EAX, the Syscall instruction is performed, and then we return. And on the other hand, we can see on the picture on the right the definition of the function with the exact same function signature, just as in WinAPI, while using the extern C macro to order the linker with some additional project configuration, use the function on the left as the implementation for the definition on the right. So this is Direct Syscalls in a nutshell. And this used to work very well because at this point, we're not hitting any hook functionality. We're avoiding using NTdll at all. And this used to work very well until it didn't. At some point, somebody caught on, and some mechanisms started detecting this a bit more, and it became a bit harder for us to keep using Direct Syscalls in the same way. It was a big roadblock, but it resulted in very healthy results. The first thing we thought about is that we still needed to perform syscalls. For example, if we still want to perform injections, we still need to operate in the same way. The second thing was that we need to really take it into our heart that Direct Syscalls don't work in the same way they used to. And the third thing was that even frameworks that use Direct Syscalls are detected as well. So the most common framework for using Direct Syscalls, for example, is SysWhispers, and we saw that code that contains that C-generated code from SysWhispers has been detected as well. And we sat and we thought about it for a long time. Me and my team leader, Kobe, we sat and had some very healthy arguments about how we can make this work again, how can we make it a bit more creative and a bit less detected. And we came up with 3 ideas that assisted us with getting to the final result. So the first idea was you cannot detect a function call if no function is called. So we imagined to ourselves one researcher sitting at his desk and saying, okay, if I find a call instruction that results in a syscall outside of NTdll, this is a detection. And so this was the first imaginary block that we could go around. The second was that memory pattern may be able to detect patterns of syscall number retrieval. So as we mentioned, each syscall number for each function. And between Windows builds and Windows versions, the kernel is changed. So some functions are added or removed, some things are moved around, and the syscall number changes between versions. And that's why, for example, again, in SysWhispers, every C-generated code that you will get will include a function to retrieve the current syscall for the current build every time, so you wouldn't have to hard code all of them into your assembly. So this might be another point of detection. And the third idea was, and that's a general idea, is that memory pattern is consisted of a sequence of hex characters. So if we provide less data, there's less things to detect, harder it becomes. So with these 3 ideas, we continued to think, and then we came up with the idea of using inline assembly. So inline assembly has provided us with the following. It allowed us to replicate the syscall through inline assembly without actually generating a function call. So this is one, and it's very important. The second is that if we could reverse engineer the fast call convention for how we call a syscall, then we can pass the arguments in that same inline assembly snippet and maintaining the exact same functionality. As a side note, the fast call convention is how in C language arguments are being passed to the correct registers and to the stack. So knowing that, we started working on it, and we understood that we really needed to boil down the existing Direct Syscalls flow as we know it. So before using inline assembly, this is how it looked like. We used to call the function that we defined For example, NT-allocate virtual memory. Excuse me for the typo. We provided it with the handle object, with allo as our allocated memory address, with file size as the size of the allocation we want to make, with memcommit and memreserve as the allocation type, and with page execute read write for the section permissions. Under the hood, when we debug this, we can see all of the arguments being passed to their correct places. So we can see the handle object being moved to the RCX register. We can see the file size being loaded into R9. We can see 40 loaded to the stack. 40 is the numeric value of the page execute read write macro. We can see allo being moved to the RDX register. We could see 3000, which is the numeric value for memcommit and memreserve together, being moved to the stack as well. After that, we can see the call instruction being made. And when we perform the call instruction, we jump to our external file. In our external file, we can see the logic that we have already implemented, moving RCX to R10, moving a numeric value to EAX, performing the syscall, and returning. So this was before inline assembly. And after we boiled it down, this is what we are left with. So what you see here is an inline assembly snippet that contains all of the logic that you've seen so far. So you see moving 40 to our stack, and 40 is again our page execute read write. We see 3000, our memcommit and memreserved, being moved to the stack as well. Our file size being moved to R9, our allocated memory space to RDX, our handle object to RCX, and then directly, without calling any function, losing the function call or the call instruction, we move RCX to R10, a call number to EAX, performing the syscall, and then as a final touch, we move the value of EAX to our NT status variable, as when syscalls are finished, EAX would be populated with the actual status of the syscall. So by doing this, we have completely reduced any memory pattern of using syscalls. We have lost the call instruction, and this is still not detected to this day, but I'm pretty sure that after this, somebody's going to detect it somehow. And this is it, guys. So this is the concept, and this is how we lost any usage of NTdll. We've lost hookings, and we still maintained the Cisco structure while making it a bit harder to detect. So for summary, we spoke about how DLLs were built, how they are hooked, what are syscalls, what are direct syscalls, how we can combine them with inline assembly and a bit of creativity to make something that is harder to detect. And the next steps that I would suggest taking is to learn about kernel mode hooking, aka kernel callbacks, and to learn about direct kernel manipulation. And I would suggest the Kernel Cactus project as a great resource. And that is all for today, guys. If you have any questions, I'm going to be around here, and I'm going to take them. I'm going to be around for another hour or so. Thank you, everyone. Thank you, CyberArk, checkmarks. And that is it for today.